In last video, we discussed about the Fourier transform. We saw the expression for discrete Fourier transform, and we also saw the inverse discrete Fourier transform. We also stabilized the relationship between Fourier series alpha coefficient and its linkage with discrete Fourier transform. And we saw that how alpha k is related with the discrete Fourier transform. Then we saw how to calculate the phasor, how to do the phasor estimation with the help of discrete Fourier transform, and we found fundamental phasor of a waveform can be calculated as 1 by root 2 a1 minus j b1, and the alpha 1, that is the Fourier series coefficient, can be calculated as x1 divided by the capital N number of samples. And how it is linked with a1 and b1. a1 equal to 2 times real value of alpha 1 and b1 is minus of 2 times imaginary value of alpha 1. So if we put these values, we will get the value of fundamental phasor. Now let's take one example to understand better how to estimate the phasor with the help of discrete Fourier transform. Suppose there is a signal which we are sampling 16 times in 1 second, and the value of samples are as follows. Now using these samples, we need to reconstruct the signal and find its phasor value. So this is the sample number and the corresponding sample values we have. Now if you calculate the discrete Fourier transform, the value of DFT, if you start calculating, you will get these values corresponding to the samples which we have received. Now if you divide the DFT by 16, that is number of samples, you will get the value of alphas. So alpha 1 is nothing but 0.5 minus j 0.5. So if you take twice of the real value, you will get the value of a1, and minus of twice of imaginary value, you will get the value of b1. So if you calculate, you will get a1 as 1 and b1 as 1. So if you reconstruct, you will get the value of signal, that is xt equal to 1 plus cos 2 pi f naught t plus sin 2 pi f naught t. 1 is coming because of the DC component which corresponds to sample at time t is equal to 0, that is 0th sample. So using the sample values, we can reconstruct the samples and we can find out the phasor value of the signal. So what would be the phasor value? As we saw in the previous slide, the phasor value is 1 by root 2 a1 minus j b1. If you put the value, the phasor value of this signal will be equal to 1 minus j by root 2. Now let's talk about the phasor update, how we do the phasor updation, because from the field we continuously get the signals, that is the sample data, and we have to reconstruct the phasors after the arrival of each sample. So how we'll do the continuous phasor update? Because initially we take one window of sample data and we execute and find out the value of phasor, and then after next sample we have to rerun the phasor estimation and again find out the value of the phasors. Now before going into the details how we do the phasor update, let's see how we can simplify the phasor representation into real and imaginary component. So Fourier series coefficient we can correlate, that is in continuous form and in discrete form. Now the phasor value, say kth phasor value will be ak minus jbk by root 2. So if you put the value of ak and bk in discrete form, that is what we have with respect to the continuous component. So discrete value of ak we just put from here into this, and when we simplify for the phasor xk, we can write the value of xk is equal to root 2 by n sigma n is equal to 0 to capital N minus 1 xn cos kn theta minus j sigma n is equal to 0 to capital N minus 1 xn sin kn theta. So we can clearly distinguish between real and imaginary component. Let's assume the real component is xkc and imaginary is xks. So what we can write, xk can be written as xkc minus jxks. Now how we do the phasor update? We utilize two techniques. One is non-recursive technique and other is recursive technique of phasor updation. Now let's understand first the non-recursive technique of phasor update. So initially we will take 0 to n minus 1 samples for phasor estimate. So let's see this waveform, that is sinusoidal waveform, and we start taking samples from time t is equal to 0, and the number of samples we take up to n minus 1. So we will take the samples from n is equal to 0 to n minus 1, and we will utilize this window to estimate the phasor. Let's say that at this point the 1 pps signal is coinciding. So with respect to standard waveform, this sample, that is n is equal to 0, is having a phase angle difference, say phi, and the theta is the sampling angle. So the first sample, that is n is equal to 0 sample, will be of angle difference phi with respect to the peak of the sinusoidal signal. The second, that is at n is equal to 1, the signal will have a phase difference of phi plus theta, and so on. Now at nth sample acquisition, the phasor estimate needs to be repeated, and this has to be repeated now for sample n is equal to 1 to capital N. So what will happen in that case? The window 1, which was taking samples from n is equal to 0 to n minus 1, will now shift by one sample, and in the window 2 we will take samples from n is equal to 1 to n is equal to capital N. So we will shift the window by one sample and recalculate the phasor value. So now the fundamental phasor for 0 to capital N minus 1, that is window 1, will be given as x n minus 1, and we can represent it as equal to root 2 by capital N sigma n is equal to 0 to capital N minus 1 xn cos n theta minus j sin n theta. Now for window 2, when the sample is taken from 1 to capital N, the phasor value, say it is xn, will be given as root 2 by n sigma n is equal to 0 to capital N minus 1 x n plus 1 cos n theta minus j sin n theta. So now what is happening, if you compare these two phasors, the second phasor is advancing by one sample. That means the second phasor will be lagging with respect to phasor 1 by angle theta. So Now as the data window advances by one sample, the phasor will rotate in the counterclockwise by angle theta that we saw in the previous slide. Now since the phasor calculations are performed fresh for each window without using any data from the earlier estimates, the algorithm is known as non-recursive. So non-recursive algorithms are numerically stable because every time we take the sample as if it is directly coming from the field, that is, we take them as a fresh sample and recalculate the phasor. So for 0 to capital N minus 1, first we will calculate the phasor, and then again we take sample from n is equal to 1 to capital N, and then we again recalculate the phasor. So in that way we will not utilize the calculations for phasor between n is equal to 1 to capital N minus 1. So it means that we are considering every sampling window independent to each other. So in that case, what is happening? We are wasting the computational effort because every time we are starting our calculation from fresh, and for each window the calculation is done independently without utilizing the samples which are common in both of the windows. So old sample data is discarded and fresh data is acquired every time to estimate the phasor value. In this way, the phasor will keep on rotating with a constant magnitude and sampling angle. So this is what we have the disadvantage when we utilize the non-recursive phasor update, but it is numerically stable. Now let's talk about the recursive phasor update. So let's say initially the window is from 0 to capital N minus 1 for phasor estimate. At the nth sample acquisition, the phasor estimate is repeated from sample n is equal to 1 to capital N. Now fundamental phasor for sample 0 to capital N minus 1, that is window 1, we can write as root 2 by n sigma n is equal to 0 to capital N minus 1 xn e to the power minus jn theta. So that is in the Euler form. Now for window 2, what we can write? We can write, say, if this is xn, we can write the fundamental phasor for window 2 is root 2 by n sigma n is equal to 0 to capital N minus 1 xn plus 1 e to the power minus jn theta. Now instead of recomputing the above phasor, that is phasor in window 2, we will compute this phasor by reusing the samples from 1 to n minus 1 which is there in the window 1. So how to use it? Let's do one thing. We multiply the fundamental phasor of window 2 by e to the power minus j theta. So what we can write? We can write it is as root 2 by n is equal to 0 to n minus 1 xn plus 1 into e to the power minus j n plus 1 theta. Now let's define this new phasor as x cap n. So in x cap n, what we will do now? We will add and subtract the value of root 2 by n x naught e to the power minus j 0 theta. So we will add and subtract. So when we add and subtract, it will not have any impact on the value. Now let's see what will be the value of x cap n. So what we can write? X cap n can be written as xn minus 1 because what is there in the bracket is nothing but the value of phasor which was estimated in window 1. So we can assume n plus 1 as, say, another quantity k. So whatever we get will be just same as we have in case of phasor estimation in window 1. So we get xn minus 1. Now the next value is root 2 by n x naught e to the power minus j naught theta. Now since 0 and n, the values are interchangeable because those are the sample after one period, so both will remain same. So we can replace 0 with capital N. So 1 0 we are replacing with capital N, and another 0 will remain same because e to the power minus j0 theta is nothing but e to the power minus j n theta. So the nth, that is capital Nth sample and the 0th sample will be same if we are sampling at a constant frequency. So what we can write, x capital N is nothing but the xn minus 1 phasor plus root 2 by n xn minus x naught e to the power minus j0 theta. This value is again equal to 1. So what we are doing here, we are adding nth sample and removing the 0th sample. So now n samples span exactly one period of the fundamental frequency. But you see here, this x cap n defined by the above equation differs from the non-recursive estimate by angular retardation of theta, because there instead of n theta we are utilizing n plus 1 theta. That means we are delaying the sample, that is xn in the previous slide, we are multiplying it by e to the power minus j theta, means we are retarding the overall sample by angle theta. So what we get now is x cap n with angular retardation of angle theta. So if you add the nth sample and remove the 0th sample in window 2 and use the recursive update, you get the phasor which will have the angular retardation of angle theta, and the advantage by using this is that it makes the phasor stationary and not rotating with the sampling angle as we see in case of non-recursive. So in general, the recursive algorithm is numerically unstable because we are reutilizing the sample n is equal to 1 to capital N minus 1, which makes this kind of recursive update numerically unstable, because if there is any error in sample from n is equal to 1 to n minus 1, the same error will be reflected in the next window also. So from window to window, the phasor estimate, if we do using recursive update, the error will keep on propagating. So because of that, this error will always present in all the phasor estimates which we are doing from window 1 and so on. So because of the great computational efficiency of the recursive algorithm, it is usually the algorithm of choice in many applications, because the speed of data refresh from the field in case of PMU is very high. So the phasor estimate also has to be done at very fast pace, and the recursive phasor update offers that kind of opportunity because it will give you the fast computation of the phasor estimate.